this thermometer actually says the degrees in Celsius, and it says 25 degrees Celsius. Okay, I can read it and say, oh, that's 25 degrees Celsius. You don't have to understand how Celsius converts to Fahrenheit. You just read that number that thermometer actually tells you. Then the judgment that the temperature is 25 degrees Celsius is evident, because I can verify it by looking at the thermometer and saying, yes, it is 25 degrees Celsius. So what does this mean for objects like propositions or programs? It means that we want to make judgments about propositions and define when these propositions satisfy a particular property that can be then verified. So what would be judgments in our view? Okay, so here are a couple of the judgments we're mostly concerned with today. It is a judgment and we'll say a WF, which says a proposition A is well formed. We're also concerned with a true later today, okay, which is saying a proposition is true. And so while the first part is about the syntax, the second part is about the meaning. So these are the ones we are mostly concerned with today. I'm going to put them here in blue. But there are many others I could imagine. So for example, I could imagine a judgment that says A is true at a given time. Or I could imagine a judgment that says A is possible. Or I could imagine a judgment that says a proposition A is equal to another proposition B. So there are many forms of judgment I can envision. But these are the ones we're mostly concerned for this morning. And then we're defining them via axioms and principles. So the typical format of an inference rule is you have one judgment law and you have multiple judgments as premises. So these are the premises. And then the conclusions. So don't worry if this feels for some of you a bit slow, because we're going to get to more interesting stuff. But at this point, we just need to have a sort of common basis. Okay, so let's define well formedness. Okay, so I want to define A as well formed. Well, there are two rules in some sense. Okay. Top is well formed. So I'm writing the name to the right of them. And I have another rule which will say if A is well formed and B is well formed, then I can form A with some kind of operator, B is well formed, where I have as operators binary things, so and or an implication, and they're all part of what it means to be an operator. So this is an axiom, and this is a rule of inference. So this class just talks about the syntax, okay? But we're more interested actually in defining the truth of something. All right, so now how do we define a truth? Okay. So that means a proposition is true. And the important principle Jensen defined, or had as a guiding rule, essentially, time was that we define the meaning of such a proposition, or the truth of a given proposition, by introduction and elimination rules. Okay, so, parts, the introduction rule. It introduces the connective. Okay, connective is and or imply top is a something. And the elimination rule says how you can use this. How to extract or synthesize information out of a given connector. So the meaning of a given proposition is really defined just by the connective itself. Okay? It's not, I'm defining conjunction not by referring to disjunction. I'm defining implications simply by the notion of implications. Okay? And when I define disjunctions, I will define it only by looking at disjunction, not referring to implications. I'm going to have them all sort of individually defined, okay, as compartments. So it's very modular. So the first simplest thing we're going to define is truth, top. So top as a proposition internalizes this notion of something being true. And there's only one infinite rule which introduces it. Okay, so that's a top introduction rule. Because there's no more information that we could possibly get out of top. Okay. All we know is true, and then there's nothing more we can get out of. Okay. True is true, top is top, everything is top. Okay. So maybe we look at conjunctions to sort of see how this introduction and elimination principle comes in. Conjunction. So A and B is my proposition. So how would I introduce a proof for A and B? Okay, so when is A and B true? Well, I might say that if I have a proof of A as being true, and I have a proof of B as being true, I have two premises, then I can establish a proof of A and B being true. Okay, so that's my A introduction rule. And you might notice that it internalizes this principle of and. Okay, so I talk about and, but the and often comes in either as part of the proposition, so when I write the then. But I might also say I have a premise A true and I have a premise B true. In this case, the and is actually like more a meta operation, right? I'm talking about. And so the fact that I'm having here this symbol, it internalizes in my language of propositions this operation and. Right? Okay, so how should I use the fact that I know A and B is true? So if I know A and B is true, what is the information I can extract from it? Anybody? Yeah?
B is true.
That?
B is true.
B is true. I like B because it's the first letter of my first name. B is true. Okay. So it's the left side. No, it's the right side. Okay, of this conjunction. So we're going to call this and elimination to the right. But you know, we shouldn't forget. We should also be able to get out A is true. Okay. So we really need both rules in order to get all the information out that seems to be present in such a conjunction. Now, I will talk about how we can make sure that these rules sort of make sense, right? And why I would need the second kind of rule as well. Because, of course, an important question that we wanted an answer is, how do we know, that these rules now make sense, right? I said at the beginning, well, I have a bunch of, previously people had a bunch of axioms and we didn't know whether these were good axioms. So now you might say, well, how do I know these are good rules? And, in fact, some of you might have come up with a very different conjunction rule. the only way I could define this conjunction elimination. So why should I pick this over something else? So logic, what I want to really instill in you isn't something God-like given. Logic is something that describes sort of our reasoning processes. And how we reason about things is, depends. Right? So this is one way, which is probably a legitimate way. So what's the simplest kind of way of proving things? Okay, so essentially everything is top. Okay, so let's say I want to prove top and top and top is true. And I want to know whether this judgment is true. Okay? Well, you have to verify it. And that means we now need to use a sequence of these inference rules to actually justify why this is a true statement. And so I can justify this by first using the and introduction rule, which means I need to prove top is true, and then I need to prove top and top is true. And I know top is true because I have the top introduction rule. And I can use and introduction again, and I need to prove top is true and top is true. So yes, everything's top. Okay? And my derivation tree here ends essentially with these axioms that say something that was truly evident, namely that top was. Now that's nice, okay, but you want to probably say a few more things than just about top. Okay, so you might say, well, can't I just generalize this and argue that from the fact that I have A and B and C, can I then derive B is true? And how would I do that? Yeah?
Elimination.
You use some eliminations, okay? So we'll first want to get out the side of the proof, okay, of the conjunction. Okay, so we're going to use and elimination to the right. Okay, that gives us B and C is true. And then we use and elimination to the left, which gives out the B. Move this a little bit up. So this isn't yet a full proof though. And we seem to have said, assume that we somehow know A and B and C is true. Okay. This part here seems to be completely unjustified. Where is this coming from? So really what you're saying here, you want to say assume this, okay? So make an assumption that's labeled U, okay? So this is essentially saying assume the assumption called U, okay, which stands for this guy. And under this assumption, we establish B is true. So this is essentially saying, given A and B and C, prove that B is true. And this sequence of inference rules justifies, right, how we can, from this assumption, arrive at this judgment that B is true. Now, what we would like to do, though, is we would like to internalize this kind of reasoning, okay? Because what this is essentially is what we call a hypothetical reasoning. This is even weaker. Let me try and get a blue one. Or green. Green is always good, right? So this is a hypothetical reasoning. This is not any better. My black one. So hypothetical reasoning essentially says by assumption, or hypothesis is the same name as saying I have an assumption. And that means now I want to internalize this hypothetical reasoning by using essentially an implication sign. And the rule we're going to use is an introduction form of this symbol that will introduce this assumption U. So I'm going to label the assumption as being introduced, and the scope of this assumption is essentially exactly until here, until we internalize it here in the symbol. So hypothetical derivations are essentially of this form. You have a bunch of judgments. Hypothetical. Some names. Okay, and we're deriving something, J. Okay, here we have one assumption, deriving one fact. And then we're internalizing this at some point by some kind of other. So this is a valid proof, okay? But the previous one was not, because it didn't justify where this assumption was actually coming from. Questions? Yeah?
You have some markers here.
Some more markers, okay. Give me more markers.
They're a bad batch.
But they're your data.
There are many markers.
And many markers. So many markers. There are more markers over there. I should dispose those that are just. I'm going to have here a little graveyard of markers. Okay. I'm sure more markers help. Yes.
In the derivation we just took now, the second one should be EL, right?
EL. Very good. Excellent. Somebody's awake this morning. Not me, but left. Thank you. Yes?
Does the proposition need to be well formed for us to judge it as true?
Yes. So we will assume that the proposition is well formed in this setting here before we judge it to be true. However, again, sometimes we define, in richer systems, we might define it intertwined. Yeah? Last row on that one.
Sorry, could you just speak up even more?
Even more. Yes, I can definitely speak louder. Yes.
How do we know that, for example, A conjunction B and B conjunction A name different propositions rather than naming the same proposition?
So you want to have A conjunction A.
No, A conjunction B and B conjunction A.
A conjunction A. And B, sorry, is that different from B and A? Yes?
Yeah.
Okay. Well, so when I make a statement such as this, okay, A and B and C, it's certainly, this A is sort of unique. So if I wanted to prove A and B, and this is actually proving B, there's another error. My goodness. So this B and this B must be certainly the same. Okay. So you can think of this as saying, yes, for all A, for all B, and for all C, A and B and C implies B. And in this sense, I could have said also F and G and D implies G. So within a given proposition, the names are unique and meaningful. Okay? However, when you state it, I could have renamed it. Does that make sense? I could certainly prove that A and B implies B and A. Okay? I'll leave that to a little exercise for you, because I want to. Well, I first need to give you the rules for implications. I haven't actually given you the rules for implications. But that's a good question, right? Like, what does it mean when we make such a statement? And does it matter that we, say A and B and C implies B, or if we could have said F and G and H, let's say, okay, implies and G. And these two propositions are for us the same. But an important question will be, when are two propositions equal? Okay, and so I'm going to talk about that tomorrow or the next 2 days. So in propositional logic, we're like in I picked the easy lecture. I leave the hard bits to others. Yeah?
Is there a reason why you use the
Horseshoe?
sorry?
The horseshoe?
Yeah, the horseshoe instead of like an arrow or anything.
I like the horseshoe. It goes back to Gensen. Okay. There's no particular reason. Okay, so what are our introduction and elimination rules? For implications. So the introduction is really internalizing this hypothetical reasoning. Okay, so essentially if I have an assumption A true, and I have a label for it, U, I have a bunch of inference rules, and I derive B is true, then I can conclude A implies B is true. Okay, and as I mentioned, I have this label U here, which will say, if you read from bottom to the top, it means you're introducing this assumption, A true. If you have taken a logic class or you've seen the natural reduction system, actually, Gensen thinks of this more as top-down. So you make an assumption and then you discharge it. And once it's discharged, it is actually sort of internalizing this implication. Either way, this assumption ceases to exist after this line. It does not exist after this line, so it is introducing a notion of scope that you might be familiar with from programs. And what is the elimination rule for it? Okay, the elimination rule says, well, if you have A implies B is true, and you have A is true, then we can conclude B is true. Okay, so that is how we get the information out of this implication. Namely that, that we can extract the information that B is being true. Okay, so far so good. Now, it's a little, yeah?
So, this is what we call like a hypothetical style of doing it, right? So, because immediately what I think about is context.
Yeah?
And that's
Well,
like something.
You're ahead of me?
That's something else completely, right?
Huh?
That's something else completely, or?
No, I'll get there in 2 minutes.
Oh.
The next thing I want to talk about. So because here, again, this hypothetical reasoning, you might say, well, what is the status of these assumptions? Okay, we are reasoning by assumption. Okay, sounds good. Okay, that seems like a simple proof. Simple enough. Okay, but what are the properties we have for assumptions? So for example, if I want to prove A implies B, implies A being true, yeah, we believe this is true, right? If I say assume A and assume B, you should be able to conclude.
So
A.
this means we can assume A and B separately, or does it mean we assume A implies B?
You assume A, and then we'll assume a B, okay? And now you have two assumptions, okay, A and B. And then I ask you, is A true? And your answer is going to be? Yes. Okay, that was a very timid yes. Okay, good. So, right, and so how do I justify this? Well, I I justify this by introducing first my assumption A being true. Okay, and now I need to prove B implies A being true. And I will introduce another assumption. Oh, there's a purple marker, I'm very excited. That says B is true. Okay, I'll put that on the side because it's not really needed for establishing that A is true. So I needed to prove A is true, I immediately refer to my assumption U, I'm done. But that means that this assumption here is unused. And that's typically okay. And when you reason, when you build mathematical proofs, you can have additional assumptions. Okay, maybe that's not nice, but it certainly doesn't alter the truth of the proposition you're trying to prove. So, so that brings me to a very important property of assumptions, namely the property that you have weakening. Which essentially says assumptions don't have to be used. Or you can think of this as additional assumptions don't do any harm. They're sort of harmless. You can always add them, but they don't alter the meaning. Yes?
At the moment, it seems like every well-formed proposition is true because we don't have a false value.
Oh, well, but there are some things you still can't prove. So, for example, you cannot prove A implies B and C. I have no way of actually saying that this is a true proposition.
Can we not do induction on B?
Huh?
Can we do induction on B?
Can do induction on B. So far I haven't even talked about induction. Certainly you cannot prove this simply by the rules of inference. It's true we don't have false. Okay. I'm very deliberately not really talking about false. Okay. I like to think positive, that's my short answer. But we can talk about a longer answer, yeah?
So, in all the previous examples, sort of everything has a place to live that's very, like, I can see the tree very clearly. In that one, I'm a little confused where the B is true live, because,
Yes.
yeah.
Yeah, exactly, right? So this is good. Good observation, right? Where does B live? B true live, okay. So this two-dimensional representation is sort of, it's nice, it's economical, okay? But it is also a little unclear, like where does this live, right? Okay? In some kind of space. So context will be the answer, okay? But before I go to context, I'm going to talk about another property of these assumptions, which is essentially the fact that you can use assumptions more than once. Okay? So you can use A to prove A implies A and A being true. Okay, so how would I prove that? Well, I need to prove A and A being true. I might take an introduction. Okay, so that's my assumption, and I need to prove twice that A is true. So what I'm doing is I'm actually duplicating it. Okay, I'm using it twice. So I'm using it here, and I'm using it here. And that's where it was introduced, or where it was discharged. Yeah.
So a letter just next to the line of inference indicates where you're introducing an assumption, and a letter next to like a named inference rule indicates where you're eliminating it. just notational?
This is where it gets introduced.
Oh, that's
So
fine.
the up superscript next to the name of the rule name tells me it's being introduced.
Mhm.
The letter next to the line is essentially saying it's the name of that rule of inference. It's a justification. So since now I have not, I don't have a fixed name for assumptions, they just label U, W, whatever. Essentially there will be a flexible number of axioms because of that. Does that make sense?
Yes.
Yeah?
What do you have above A is true there?
There's a not properly erased part. Yeah,
If you replace one of the top views with a W, then would you be using?
I don't have W.
Sorry.
Yeah,
Oh,
I have W.
I see.
Okay. But maybe what you're getting at is I could have a proof that says A and A. Okay, A and A. Prove A. Now, there are many different proofs for this. Okay. So, yes, I need to prove that A is true. But, there would be different kinds of proofs. Because you could get out the first part, okay, so you could say, I justify this by and in elimination to the left, but you could equally say, I'm going to justify this by and elimination to the right. So it's not true that a proposition has a unique proof, okay, that's for sure. And the same thing holds for these assumptions. I might use one assumption in different ways. And especially if I applies the same assumption. So I could rewrite this proof and say, can I prove from A implies A being true? Okay. So now I introduce the assumption A being true. Okay, and I need to prove A implies A being true. And I now need, let's say even better, to prove A implies A implies A and B, A and A. So now I have the second assumption, A true, which is maybe called W. And I need to prove A and A being true. Okay, so now there are many ways, okay? I could prove this. Yes. I could use twice this assumption, I could use twice this assumption, I could use for the left A this assumption and for the right A this assumption, or vice versa. Okay, so there are many, well, there are 4, I think, ways to finish this. You can fill in the different